So the goal for today is to analyze Newton's three laws of motion in detail. If you guys remember, about a couple of weeks ago, or a week and a half ago, I posted this video on Edpuzzle for you guys to watch. And this guy basically just gave you guys an introduction to Newton's three laws of motion. And he gave you some examples of these laws applied in our everyday lives. What I want to do today, I want to kind of elaborate more on these laws and talk about them more in detail and open the door for questions in case you guys are confused on something and you want to be able to ask me. Okay, so if you go to Schoology, now right now I haven't uploaded the folder for fourth period, but as soon as class is done, I'm going to upload the folder for today for fourth period. And in that folder, this is what you guys will see whenever I get the folder actually published in Schoology for this class period. But you guys are going to see this. There's going to be three short video clips that involve Newton's three laws and kind of explaining them in detail. There are some notes on Newton's laws of motion, and we're going to go over all these notes on today. And of course, we're going to finish the class with doing a few example problems using Newton's second law. And of course, and then I'm going to open up the assignment for you guys to complete. So that's what's on the agenda for today. Okay. Remember that that lab that we did last week, that virtual lab? That virtual lab, in case you guys don't know, really involved the details of Newton's second law, which we're going to elaborate more on today. Okay, so let's begin with Newton's first law of motion. I'm going to click on this YouTube link, and we're going to watch this video together. And then as soon as we get done with this, we're going to watch the other two before we get started on going over everything that's important. Okay, let me make sure you guys can hear. Let me turn on my my computer sound for you guys. And guys, please be paying attention to this video because some of the questions in the homework for later on will involve you guys really understanding these concepts behind these laws.
Welcome to the European Space Agency ESA. This is the Robotic Learning Centre, and I'm here to help you find out more about Newton's three laws of motion. Maybe you've heard of Newton before. He is the scientist who got hit on the head with an apple. At that time, he was studying motion, trying to understand the concepts behind it and how they relate to things we experience in everyday life. When Newton recovered, he realised something important. He already knew that an object accelerates only when a force acts on it. Therefore, if the apple were moving, it could only accelerate if there was a force acting on it. He called this force gravity, and to this day we measure all forces, including gravity, in newtons. Newton came up with three laws of motion, laws that describe how forces and objects relate to each other. To help you out, I've asked some friends in Barcelona, Dublin and Erlangen to demonstrate the laws. I've also asked astronauts on board the International Space Station to help us. That's the ISS for short. So we're going to hear from Pedro Duque and Alexander Caleri. On board the ISS, gravity has very little effect, so everything there is almost weightless. Hi, Pedro. That's a nice smile you've got there, Pedro. Not much is happening. The ball is just hanging there in midair. Pedro blows on it and it moves because of the force of his breath. Now the ball is moving again, except this time Alexander has stopped it with his hand. And this time, nice move. Pedro changes the ball's direction by applying a force. What you've been seeing are illustrations of Newton's first law of motion. This states that every object in motion or at rest remains in that state unless an unbalanced force is applied to it. The state of motion is the speed and also the direction. The two combined, speed and direction, are what we call velocity. An object at rest has a velocity of 0, and it stays at rest unless acted on by a force. We call this tendency inertia. Here you can see Pedro applying a force to the ball. He is changing the ball's direction, therefore changing its velocity. In the second experiment, you see Alexander stopping the ball. Here he's changing the speed, therefore he's changing its velocity. The rate of change of velocity is called acceleration. Let's see what our schools have to show us. Pushing the skateboard, that's a force, isn't it? The skateboard moves, hits the pillar and changes direction. But the apple keeps going. That's because this time the force is only applied to the skateboard and not the apple. That's why eating in space isn't easy. The spoon stops, but the food keeps going. Ooh, that looks nasty, and that's why we use seatbelts. If we were in a weightless environment like the ISS, then he would continue to move, but on Earth, gravity pulls him back down. Okay, here we go again. That looks really messy. That's why we have to use lids on takeaway coffee. Thanks, girls. Good trick. I'm sure I don't have to say, don't try this at home. Looks like she's getting her teacher in to help. That apple's not going anywhere. I mentioned objects at rest, didn't I? In these experiments, the apple, the pencil, and the girl on rollerblades are not moving. They're at rest because the forces acting on them are in balance with each other. But when the support is removed, the force of gravity, now unbalanced, pulls them to the ground. Without the force of gravity, they would just stay afloat, just like on board the ISS. So, that's Newton's first law. An object at rest stays at rest unless acted on by a force. And an object in motion will stay in motion unless acted on by a force.
Okay, guys, that was the first of two clips I'm going to show you guys today. And of course, that one was the longest. But as you guys saw, that was an excellent demonstration of Newton's first law. Hold on, guys. Let me try to get out of this YouTube. And of course, I also have that law written down in the notes that is currently posted to Schoology. Says that Newton's first law, which is also called the law of inertia, this law states that an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. That's important. I'm going to highlight that an object in motion stays in motion with the same speed and in the same direction. Just like I can highlight. Unless acted upon by an unbalanced force. That's very important, guys, that you guys know that if no unbalanced force acts on your moving object, then your object is going to be moving at a constant velocity, or in other words, a constant speed that is moving that is maintaining motion in the same direction. So basically what that's saying, guys, imagine if I was in outer space. So I'm in outer space and I'm far from any sort of gravitational field. Or far from any strong gravitational field, I should say. Like, imagine that situation that I had a football in my hand. Okay, if I had a football in my hand and I threw that football, Newton's first law says that football is going to keep going forever and ever and ever and ever and ever without end, unless a force stops it or either decides to divert its path of motion. Okay, but if there's no force to interact with it, the football is just going to keep traveling at a constant speed forever. And by the way, guys, you saw that in your lab. Hopefully, you guys saw Newton's first law demonstrated in the lab. Even though this lab focused mainly on Newton's second law, notice that whenever we turn friction off, notice how as long as the man is pushing on the object is speeding up, is accelerating. But the moment that the force stops, what do you guys notice about the speed? The speed just stays what? It stays constant. So as long as there's no force acting on this box, the box just keeps moving. It just keeps traveling at a constant rate forever. I'm going to say that again. Notice as long as the force... Hold on, let me turn friction off. Again, notice as long as the force is acting on the box accelerates. The speed continuously increases. So the speed just continuously increases. The moment that you stop pushing on the box, the speed of the speed of the box stays constant. Okay, so that's Newton's first law in action. An object in motion stays in motion at a constant velocity unless acted upon by an unbalanced force. Okay. Now, moving on to Newton's second law. Let me go back to my notes here. Guys, give me just a second while I pull up these notes in Kami. That way I can write on them. Okay, so we discussed the first law. Now, let's look at the second law. Newton's second law of motion says that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. Okay, so guys, this law, sometimes you will see it written in this mathematical form. And it looks just like that. Force is equal to mass times acceleration. Force is equal to mass times acceleration. Basically, what this law is saying is that forces causes objects to accelerate. Force is equal to mass times acceleration. This is an important law, or in other words, an important mathematical equation that we're going to be using again and again and again in this course. So be sure you guys know this. Okay. Some of the homework problems that you're going to be working on later on will deal with this particular equation. Okay. Guys, sometimes you will see this equation written in this form where it's rearranged, where if you take this equation and solve for acceleration, in other words, you get acceleration by itself, then acceleration is equal to force divided by mass. Again, sometimes you'll see the equation written in this form, which is, the same thing as this, just a different form. But they're both equations are saying the same thing. Okay. On last week, we did a lab. Oh man, crap! I didn't mean to close that. Let me open that back up. Hold on, guys. Let me open this file back up again. Okay, guys. On last week, we did a lab, and in that lab, we discussed the relationship between acceleration and force, and the relationship between. Hold on, guys. Let me stop sharing my screen for a moment. Hold on. Give me just a second while I delete these annotations from our previous class. Hold on. Guys, for those of you guys that need the attendance form, I just put it in the chat box again. Okay, so on last week, we discussed the relationship between acceleration of force and the relationship between mass, between acceleration and mass. So, let's start off with the first relationship. We were comparing force with acceleration. Can someone tell me from that lab what happened to acceleration as the magnitude of the force was increased? Can someone tell me?
The acceleration increased as well, right?
The acceleration also increased as well. Guys, whenever two variables are related to each other in that way, in the sense that as one increases, the other also increases, there's a name that we have for that relationship. We call that a direct proportionality. In other words, force and acceleration are directly proportional to each other. So I'm gonna write that term down because you guys are going to hear me saying that a lot this year. We're going to be dealing with that a lot. I'm going to say that again, guys. Whenever two variables in this course are related to each other in such a way that as one increases, the other increases as well, we say that those two variables are directly proportional to one another. So that's a direct proportionality. That's what directly proportional means. As one goes up, the other goes up. Okay? So that's a term you guys need to remember. Okay. Someone tell me, what about the relationship between mass and acceleration? What happened to acceleration as mass increases? So what is the relationship there? Anyway?
The acceleration decreased.
The acceleration decreased. Does anybody know what the name of that relationship is? Okay, so I'm sorry.
Nothing.
Okay, physicists say that whenever two variables are related to each other in such a way that as one increases, the other decreases, we say that those two variables are inversely proportional. So I'm gonna write that term down because again, I'm gonna say that a lot throughout this year. Okay. So everybody got that? Whenever one goes up and the other also goes up, that's what's known as a direct proportionality. Whenever one variable goes up and the other variable goes down, that is what is known as an inverse proportionality. Everybody got that? So mass is inversely proportional to acceleration, meaning as mass increases, acceleration then decreases, or acceleration drops. Force is directly proportional to acceleration. Basically, what that means is as force increases, acceleration likewise increases. As one goes up, the other goes up as well. Okay, so be sure you guys know those terms: direct proportionalities and inverse proportionalities. Okay, and guys, basically that's all that Newton's second law says. Newton's second law tells the relationship between acceleration and force and the relationship between acceleration and mass. And for example, you guys can see that equation, you guys can see that relationship clearly in this equation, that as mass increases, acceleration decreases. Let me show you guys that right now. And again, I'm gonna show you guys this before I put on that second video. Just trying to erase. I didn't mean to erase all that. Right. And again, I want to show you guys a mathematical example of the relationship between mass and acceleration according to this equation here. Suppose I have an object where I apply 1 Newton force to the object, and my object has a mass of 2 kilograms. In this case, it should be obvious to you guys that the acceleration is 0.5 meters per second squared. Okay. But what if I have another object? Let me make this bigger. What if I have another object? And I'm gonna put this object here in red. So what if I have another object? Let's say I apply 1 Newton force on a larger object that is 4 kilograms. In this case, guys, what is the rate of acceleration? What's 1 divided by 4?
Um, 0.25.
Yes, sir. Meters per second squared.
I'm so glad I didn't get it wrong.
Yeah. Thank you, Jeremiah. So I want you guys to notice something, guys. Whenever we're applying the same force to do different objects, the one that has the smallest mass has the larger acceleration according to the mathematical form of this equation. Acceleration is equal to force divided by mass. So 1 divided by 2 gives me 0.5 meters per second squared for my acceleration here. And here 1 divided by 4 gives me 0.25 meters per second squared for my acceleration here. Okay? So just keep that in mind. Okay, so going back to school, G. Let me go ahead and play this short 2-minute video for you guys real quickly. And again, this is Newton's second law.
Hello, everyone. I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. Let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have. So let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks, everybody.
Okay, guys, so he just demonstrated everything that I just said. The smaller mass has a large acceleration. Before I move on from this video, one of the things that I'm going to say about this video that I wish he had, just a particular term that I wish he hadn't used. Notice he said that the acceleration is faster, or the acceleration is fast. Guys, as a general rule, physicists don't like to use the term fast and slow to describe acceleration. Now, we may use those terms to describe velocity or to describe speed, but not to describe acceleration. Whenever you're talking about acceleration and you're comparing objects of two different acceleration values, you would say one object has a larger acceleration or it has a smaller acceleration. You never use faster or slower. You either use larger or smaller, or you can say larger or greater to describe acceleration. But don't use the term fast and slow for acceleration. We tend to reserve those terms for speed and velocity. Just something that I just wanted to add. I mean, you guys knew what he meant again, but we just, whenever we're talking about acceleration, you want to get in a habit of saying something has either a greater acceleration or a smaller acceleration. But you don't want to use the term it has a faster or a slower acceleration. You only want to use those terms when it comes to describing speed and velocity. Okay. All right. Let us move on to our third and final law. And that is Newton's third law. Newton's third law says that for every action, there's an equal and opposite reaction. The statement means that in every interaction, there's a pair of forces acting on the two interacting objects. The size of the force on the first object equals the size of the force on the second object. Okay, so let's look at this video here, this final video explaining Newton's third law.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now
Okay, so you guys got that? Newton's third law. So, and you guys clearly see that whenever he pushed on Joe, notice how as he pushed on Joe, Joe flies forward while he then flies backwards. Why is that? Because that's a clear example of Newton's third law. Newton's third law says that with the exact same magnitude that he pushes on Joe, Joe pushes back on him with that magnitude and force, but in the opposite direction. Okay, these forces are always equal and opposite, and they're happening at the exact same time. And guys, the same thing was also true of the basketball. You know, as he pushed on the basketball pushed back on him. Of course, we see that. Okay, so he pushed on the basketball pushed back on him. Now, the only difference in this situation, even though the forces were the same acting on both of them, what was different was the accelerations. The basketball, being a smaller mass, had a larger acceleration than this guy right here. He still accelerated, but he accelerated at a smaller rate. Okay, but the point is that I want you guys to know is that the forces are the same. If he pushes on the basketball pushes back on him. Does that make sense, guys?
Yeah.
All right. Okay. So that is Newton's three laws. And again, all of those notes are in Schoology. Okay. As well as the links to those videos, in case you guys want to go back and rewatch those videos whenever you guys are working on the assignment later on today. Just so you're clear on just so everything is clear with you all that you are interpreting these laws correctly, and you can correctly match them with the particular situation given to you in your assignment. All right, so the last thing that we're going to do today, let me go ahead and share my screen. We're going to do several problems together, and these several problems involve Newton's second law, force equals mass times acceleration. And there are 4 of these problems that we're going to work on together. So we're going to work on these, and I'm going to let you guys go. So let me go ahead and pull up Kami so I can annotate the file. Okay, so again, this worksheet just involves calculations with Newton's second law, and there will be a few examples in your assignment for later on, which will involve some of these calculations. Newton's second law, force equals mass times acceleration. Guys, whenever you are working on these questions, you always want to write out your units with your answers. Okay, so the units for force are typically in newtons. The units for mass would be in kilograms, and the units for acceleration would be in meters per second squared. Okay, and again, guys, we saw Newton's second law at work whenever we were doing this particular lab. Okay, so this virtual lab it's a really good lab for demonstrating Newton's first law and Newton's second law. Notice, guys, as long as I am pushing on the crate, guys, look at the speedometer there. The speed continuously increases. The acceleration is constant, which just means the speed keeps going up. So as long as there's a force, there's going to always be an acceleration. The moment I let go, speed stays constant. We're going to see that again. That this is clearly showing us Newton's second law. Clearly, that as long as there is a force acting on an object, the object experiences an acceleration. In other words, it's speeding up at a constant rate, as you guys notice from the speedometer. Okay, so that's clearly demonstrating Newton's second law for us. Okay. So let's look at number one. Number one says, how much force is needed to accelerate a truck with a mass of 1,500 kilograms at a rate of 2 meters per second squared? Okay. So once again, just use Newton's second law here. Newton's second law said force is equal to mass times acceleration. Okay. So plug everything in. What is the mass of our truck? Our mass of our truck is 1,500 kilograms times acceleration, which is 2 meters per second squared. So 1,500 times 2 gives me a force of 3,000 newtons. So always write your units, guys, on your answers whenever you're writing it out. Any questions? Okay, let us now look at number two. Number two says, what is the mass of an object that requires a 10 Newton force to accelerate it at a rate of 1 meter per second squared? Okay, so guys, what we're going to have to do here, we're going to have to take Newton's second law and rearrange it. So force equals to mass times acceleration. Here we're being asked to find mass. So if I take this equation, rearrange it, to get mass by itself, I'm going to divide by acceleration on the right-hand side of the equal sign. And remember, whatever I do to one side of the equal sign, I have to do to the other. So here I'm going to also divide by acceleration. So that means when I do that, mass is equivalent to force divided by acceleration. Okay. So mass is equivalent to force divided by acceleration. So with that said, if I have a 10 Newton force and the object accelerates at 1 meter per second squared, that clearly means the mass of my object is 10 kilograms. Okay. So number two is pretty easy. Number three. Number three says, what is the rate of acceleration of a 2,000 kilogram truck if a force of 3,000 newtons is used to make it start moving forward? Okay, so once again, writing out Newton's second law, force is equal to mass times acceleration. I then want to rearrange this equation and solve for acceleration. So that means I'm going to divide by mass. That goes away. Whatever you do one side, I have to do the other. So that means I'm just left with acceleration is equal to force divided by mass. So here, if my force is 3,000 newtons, and my mass is 2,000 kilograms, so if you do the math there, 3,000 divided by 2,000 is 1.5 meters per second squared. Make sense, everyone?
Yeah.
All right. One more. We're going to do one more. Number 4. This one here is interesting. What is the weight of a 0.1 kilogram apple? Let me say that again. What is the weight of a 0.1 kilogram apple? Now, here's something I haven't talked about yet in physics. Weight. Guys, it should be common knowledge to you all that in your everyday lives, if you want to know the magnitude of your weight, the only thing you have to do is obviously just stand on a scale. If you stand on a scale is telling you your weight. But what is exactly happening there? How does the scale know your weight? Well, guys, think about what force is keeping you glued to the scale. In other words, what force is pulling you down to the ground? What is that force? Yeah, that force is obviously gravity, right? Because if it wasn't for gravity, you wouldn't be pulled to that weight. I'm sorry, you wouldn't be pulled to that scale. In fact, if there were no gravity, you would probably just be floating in midair. So, in other words, what I'm trying to tell you guys is that what a scale does, a scale measures gravity indirectly, okay? Because gravity is this force that's responsible for pulling you downward on that scale. So, I'm gonna say that again. A scale measures the force of gravity indirectly. So, in other words, if you want to know an object's weight, the only thing you have to do, the only thing you have to do is know the magnitude of the force of gravity acting on that object. Okay? So if I have an object of any given mass and I want to know its weight, I just know the magnitude of the force of gravity acting on that object. So now the next question is, how do we calculate the force of gravity acting on an object? Well, I want you guys to think of something. Remember what we just said. Newton's second law says that force is equal to mass times the object's acceleration. Okay. Now, remember, whenever an object is in free fall, because of the force of gravity acting on it, that object has a specific acceleration. Can someone tell me what is the acceleration for an object in free fall? Guys, we talked about this
8.9.
It's 9.8. Yeah, 9.8. Yeah, meters per second. Yeah, you were closer, Maya. I just had a reverse. But 9.8 meters per second squared is the acceleration of gravity. In other words, any object that's accelerating in the gravitational field here on Earth has a rate of 9.8 meters per second squared. So that means is that the equation for the force of gravity is equal to the object's mass times the acceleration of gravity itself. And when I say the acceleration of gravity, basically what I'm saying is the acceleration due to gravity, in so many words. Okay, so in this case, force of gravity is equal to mass. What is the acceleration of gravity? Yeah, I just said it. It's 9.8. So basically, guys, what I'm trying to tell you is that this right here is a very important equation that we're going to be using throughout the year. That anytime we want to know the magnitude of the force of gravity pulling on an object, we just take that object's mass and multiply it by 9.8. Okay. So we have our apple here. Okay. And notice we go up to the top here. It says our apple has a mass of 0.1 kilograms. So we know the mass of 0.1 kilograms. How can we find the magnitude of the weight of the apple itself? Well, I'm going to plug in 0.1 into this equation. 0.1 times 9.8. When I do the math there, what do I get? I get 0.98 newtons. Okay. So in other words, the weight of the apple is equal to 0.98 newtons, right? And that makes sense because remember what I said, if you know the magnitude of the force of gravity acting on an object, then you immediately know the object's weight, since the scale is sort of indirectly measuring the force of gravity, right? Because the force of gravity is responsible for pulling an object downward toward the scale. Okay, so that is the weight of an apple that has a mass of 0.1 kilograms. And guys, in this class, just know that we typically express weight in newtons. I know in your everyday life you are used to expressing weight in pounds. Just know that in a physics course, physicists typically express weight in newtons. Now, of course, you can easily convert between weight and pounds if you know the conversion factor, but we're not really worried about that right now. Just know that in this class, instead of using units of pounds for weight, we typically use newtons. Any questions on how to find an object's weight if you know the object's mass? Any questions?
So you just have to do mass times acceleration.
Mass times 9.8. It's a specific acceleration, the acceleration of gravity. Yeah.
If they use the word weight.
If they use the word weight, yep. So if they use the word weight, you will have to do mass times 9.8. Because in other words, you have to use a specific acceleration, and that is the acceleration due to gravity, because that's what's responsible for an object's weight, right? The force of gravity pulling at it.
And it will always be in newtons, the answer?
Yep. For now. Yeah. I don't think I have any examples later on in the year of weight being in pounds, but you could easily convert back and forth between the two if you have to. And again, that was just something I will talk about when that comes up. By the way, guys, before I let you all go, I want to say this. Someone in my last class asked me a really good question. They said, "Mr. Taylor, what is the difference between mass and weight?" And I was like, that's a very, very good question. I was going to discuss it in the coming days, but since the student asked the question, I'm going to go ahead and answer it, because I would imagine that she's probably not the only one that was thinking of that.
One is in pounds and one is in grams, or one is in ounces and one is in grams.
Okay, but that really doesn't tell me what the difference is. It just tells me that they're different units. Well,
I thought that's what the difference is.
I mean, that's a good try, but that doesn't fully explain to me what the difference is. Well, guys, I want you guys to think about this. Mass represents the total stuff that makes up an object, right? The total amount of material that that object is made of. Remember, weight is something that depends on the gravitational force acting on that object. For example, guys, y'all see this stapler here? Okay. This stapler here obviously has mass, right? It has mass because it's made of stuff. And there's a certain amount of stuff that makes up this stapler. The key thing that you guys need to know is that the mass of this stapler is the same anywhere in the universe, whether I'm here on Earth, or I'm on Jupiter, or on Mars, or in the Andromeda Galaxy. No matter where I'm at in the universe, this mass stays the same. However, because weight depends on an object's gravitation, because weight depends upon the gravitational field pulling on the object, it turns out that the weight of this stapler will be different if I was to go to Jupiter. Okay, it would be different if I was to go to the moon. Because there's less gravity on the moon, it turns out this stapler will be lighter. Okay, so in other words, what I'm trying to tell you all is that the mass of the stapler stays the same. So the mass here on Earth is the same thing as the mass that makes the mass of the stapler on the moon. However, just because the masses are the same does not mean that the weights are the same. Again, this stapler will actually be lighter on the moon. In fact, if you were on the moon, you would actually feel that it'd be lighter. It'll be lighter on the moon because there's less gravitational pull on the moon. So for that reason, it would have a smaller weight. Okay. Does that help make sense, guys, of the difference between weight and mass? Does that help everyone?
Yeah.
Yeah. So just something to keep in mind. Mass refers to the total stuff that makes up the object. Weight depends upon the object's gravitational field. Weight Weight depends upon the gravitational fields pulling on the specific object. Okay, so the amount of stuff that makes up this stapler, that doesn't change just because I'm on the moon. You know, the amount of stuff is still the same, so the mass is still the same. However, the weight is what changes because there's less gravity on the moon. And because there's less gravity acting on the moon, the weight of the stapler will be lighter, even though its mass is the same compared to the mass here on Earth. Any questions?
No.
I have a question. What is due today?
I'm sorry?
What is due today for
What is?
your class?
Oh, there's going to be an assignment that I'm going to post in Schoology. It's like 12 multiple choice questions, and it involves mainly matching Newton's laws and also a few calculations with Newton's second law. As soon as I'm done with this class, I'm going to make that folder and that assignment available to you all. Any other questions? All right, let me stop recording.